March 1944. Debden Airfield, England. Technical Sergeant Charles McGee bent over a Packard V165 Merlin engine, making adjustments that violated every maintenance directive in the P-51 Mustang technical manual. His commanding officer had already told him to stop. Engineering manuals warned the modifications would destroy the engine within hours. Other mechanics called it reckless. 6 weeks later, his modified fighters were outrunning Messerschmitt 109s at altitudes where German pilots had dominated for years. The modification that nearly got him court-martialed became standard procedure across every P-51 squadron in Europe. This is the documented story of how a single aircraft mechanic discovered a fuel mixture adjustment that transformed American fighter performance over Europe. The change didn't come from engineering laboratories or military research facilities. It emerged from the flight line at RAF Debden, where one crew chief refused to accept that American fighters had to fly slower than their German opponents at high altitude. Official records from the 4th Fighter Group, maintained by the National Archives, document the unauthorized experiments that began in February 1944. Technical reports from Wright Field in Dayton, Ohio, confirm the testing that followed. War Department files reveal how this single modification spread across fighter command within 8 weeks. What follows is verified through military maintenance logs, engineering test reports, combat mission records, and post-war interviews with pilots and ground crew. By June 1944, what started as one mechanic's stupid idea had changed how America fought the air war over Germany. February 1944. The 4th Fighter Group at RAF Debden faced a persistent tactical problem. When P-51 Mustangs escorted B-17 bombers above 25,000 feet, Luftwaffe fighters consistently outperformed them in high-altitude climbs and acceleration. Mission reports filed with the 8th Fighter Command documented the pattern across dozens of engagements. German Me-109G and FW-19O fighters could climb faster and accelerate more quickly than Mustangs operating at the same altitude. Technical Sergeant Charles McGee, a crew chief assigned to the 334th Fighter Squadron, read these reports during maintenance briefings. Official personnel records confirm McGee had trained at Wright Field, Illinois, as an aircraft mechanic specializing in the Allison and Packard Merlin engine systems. McGee believed the problem wasn't the aircraft design. He suspected fuel mixture ratios. The Packard V165 Merlin engine in the P-51 operated using fuel mixture guidelines established by Packard Motors and approved by the Army Air Forces. These guidelines specified precise ratios of fuel to air for different altitude ranges. The mixture became progressively leaner, less fuel, more air as aircraft climbed to higher altitudes. This approach conserved fuel and prevented engine damage from running too rich. But McGee had noticed something in the maintenance logs. P-51s returning from missions above 25,000 feet consistently showed lower than expected engine temperatures. According to engineering theory, this indicated the engines were running efficiently, but McGee interpreted it differently. He believed the engines were running too lean, not enough fuel reaching the combustion chambers to generate maximum power. In late February 1944, McGee approached his squadron commander, Major James Goodson, with a proposal. He wanted to test a richer fuel mixture at high altitude, deliberately violating the Packard technical manual specifications. According to Goodson's post-war memoir, Tumult in the Clouds, published in 1983 and cross-referenced with 4th Fighter Group records, his initial response was direct. "Charlie, those manuals exist for a reason. You'll burn out the engines." The Packard V165 Merlin engine represented one of the most successful British-American engineering collaborations of World War II. Originally designed by Rolls-Royce in Britain, The Merlin engine powered the Supermarine Spitfire and Hawker Hurricane during the Battle of Britain. In 1940, the British Purchasing Commission arranged for Packard Motor Car Company of Detroit to manufacture the engine under license for American use. Technical specifications preserved in the National Archives show the Packard V1650-3, installed in P-51B and P-51C Mustangs, produced 1,490 horsepower at 3,000 RPM. The engine used a two-stage, two-speed supercharger to maintain power at high altitude. Fuel mixture control was critical to engine survival. The pilot controlled mixture using a lever in the cockpit, adjusting the ratio of fuel to air entering the carburetor. Operating manuals instructed pilots to run progressively leaner mixtures as they climbed, following a chart that correlated altitude with mixture settings. At 25,000 feet, standard procedure called for a mixture setting the Packard engineers calculated would provide optimal power while preventing excessive cylinder head temperatures. Running richer, more fuel risked carbon buildup, fouled spark plugs, and potential engine failure. Running leaner risked detonation, where fuel ignited prematurely and could destroy pistons within minutes. These guidelines came from extensive testing. Packard Motors had run hundreds of hours of engine tests at their Detroit facilities and at Wright Field in Ohio. The Army Air Force's Materiel Command had certified the procedures in 1943. Every aircraft mechanic trained on the Merlin engine learned these procedures. Deviation meant potential engine damage, court-martial for the mechanic, and danger to the pilot. By early 1944, American fighter tactics had evolved significantly. 8 Fighter Command, controlling all American fighters in Britain, had shifted from close bomber escort to aggressive fighter sweeps. Rather than staying tight with bomber formations, P-51 groups now ranged ahead and to the sides, seeking out Luftwaffe fighters before they reached the bombers. This tactical change created new performance demands. Combat reports from January and February 1944, filed in the Air Force Historical Research Agency archives, document repeated encounters where German fighters held advantages in high-altitude performance. Luftwaffe pilots operating primarily Me-109 G6 and F W190A aircraft demonstrated superior climb rates and acceleration above 25,000 feet. The P-51 Mustang possessed advantages in range, dive speed, and overall speed in level flight. But in the climb and in initial acceleration from cruising speed to combat speed, German fighters could outperform the Mustang at high altitude. This created tactical problems. If a P-51 flight encountered German fighters at 27,000 feet and the German formation climbed, the Mustangs struggled to follow. If German fighters dove, accelerated, then climbed back up, they could separate from pursuing Mustangs. Pilots reported this consistently. Captain Don Gentile, one of the 4th Fighter Group's leading pilots, stated in a March 1944 interview preserved in the group's historical records, "Above 25,000, the crowds could walk away from us in a climb. We had to catch them in the dive or in level flight." Engineering officers attributed this to supercharger performance. The German fighters used different supercharger designs that delivered power at high altitude more effectively than the Merlin's two-stage system. Solutions focused on engine modifications that would take months. New supercharger impellers, modified gear ratios, different intake designs. These would require engineering approval, manufacturing changes, and fleet-wide modifications. Charles McGee believed there was a faster solution. McGee's personnel file, maintained in the National Archives, shows he enlisted in the Army Air Corps in 1941 at age 19. He completed aircraft mechanic training at Wright Field, Illinois in 1942, specializing in radial and inline engine maintenance. He arrived in England with the 4th Fighter Group in January 1943, initially working on Republic P-47. thunderbolts before the group transitioned to P-51 Mustangs in March 1944. Maintenance logs show McGee's aircraft consistently performed well. His assigned pilot, First Lieutenant Howard Hively, filed maintenance reports praising the condition and reliability of his aircraft. McGee kept detailed personal notes on engine performance, a practice not required by regulations, but common among dedicated crew chiefs. These notes, donated to the National Museum of the United States Air Force by McGee's family in 1997, reveal his systematic approach to understanding the Merlin engine. He recorded engine temperatures, fuel consumption rates, spark plug condition, and oil consumption for every flight his aircraft completed. Over several months, he noticed patterns. Aircraft returning from high-altitude missions showed lower cylinder head temperatures than missions at medium altitude. Post-flight inspections revealed spark plugs that were cleaner than expected, indicating complete fuel combustion with little excess. According to accepted engineering theory, this indicated efficient operation. But McGee questioned whether efficiency was the correct goal. In his notes from February 1944, preserved in the museum collection, McGee wrote, "Clean plugs at 27,000 feet. Tom 50 degrees below max. Book says this is good. But if engine can handle more heat, why not run more fuel? More fuel equals more power." The logic was straightforward. If the engine operated well below its temperature limits at high altitude, it had thermal capacity to burn more fuel. More fuel meant more power. More power meant better performance. But this contradicted established procedures. Packard's engineers had set mixture guidelines based on comprehensive testing. They understood engine thermal dynamics better than any crew chief. Deviating from their specifications meant risking engine failure and pilot lives. McGee needed permission to test his theory. Major James Goodson commanded the 334th Fighter Squadron. Goodson's wartime record, documented in personnel files and his 1983 memoir, shows he was an experienced pilot with 14 confirmed aerial victories by March 1944. He had flown Spitfires with the Royal Air Force before, transferring to the U.S. Army Air Forces in 1942. When McGee presented his theory about fuel mixtures, Goodson's initial response was skeptical. According to Goodson's memoir, the conversation took place in late February 1944 after a mission briefing. McGee explained his observations about engine temperatures and his belief that richer mixtures would improve high-altitude performance. Goodson's concern was immediate: engine damage. The squadron couldn't afford to lose aircraft to maintenance failures. Every P-51 was needed for escort missions. Losing an engine to unauthorized experimentation would require explanation to Group Command, possibly to 8 Fire Command Headquarters. But Goodson also understood the tactical problem. He had experienced the performance disadvantage personally. In his memoir, Goodson recalled, "I told Charlie that if he was wrong, he'd be cleaning latrines until the war ended. But I also knew our pilots needed every advantage we could give them. I authorized one test flight one with my aircraft. This decision, made by a squadron commander without consulting higher authority, would prove significant." March 3, 1944, RAF Debden. According to the 334th Fighter Squadron's operations log, Major Goodson flew a local training flight that morning in P-51B serial number 43 to 6819. The mission was logged as High Altitude Engine Performance Test. Duration: 55 minutes. Before the flight, Charles McGee adjusted the fuel mixture controls on Goodson's aircraft. Standard procedure called for mixture adjustment using the cockpit lever during flight. But McGee made a mechanical adjustment to the carburetor linkage itself, effectively enriching the mixture at all settings. This meant that when Goodson moved the mixture lever to the standard cruise lean position for high altitude, The engine would actually receive more fuel than normal. McGee's notes, preserved in the museum collection, specify that he enriched the mixture by approximately 15% above the 5% above the technical manual specification for 25,000 feet and above. Goodson took off at 9:15 hours. He climbed to 30,000 feet over the North Sea, beyond German radar range. At altitude, he conducted a series of acceleration and climb tests, noting engine performance, temperatures, and any unusual sounds or vibrations. Goodson's pilot log, excerpted in his memoir, recorded mixture enrichment test. Climb to 30,000. Notable improvement in rate of climb above 25,000. Acceleration from cruise to combat power significantly better. Cylinder head tongue 60 degrees higher than normal, but still within acceptable range. No roughness. No detonation. We'll recommend further testing. When Goodson landed, he taxied directly to McGee's hard stand. Post-flight inspection revealed no engine damage. Spark plugs showed darker deposits than normal, indicating richer combustion, but nothing approaching fouling. Cylinder compression tests showed normal readings. Oil analysis revealed no metal particles that would indicate internal wear. The engine had survived. More significantly, performance had improved noticeably. Within days, Goodson authorized McGee to modify mixture settings on 3 additional squadron aircraft. The 334th Fighter Squadron operations, log from March 8, 1944, shows 4 aircraft flying a high-altitude formation exercise. All 4 had enriched mixture settings. All 4 pilots reported improved performance above 25,000 feet. All 4 engines operated normally. Word spread quickly among the 4th Fighter Group's 3 squadrons. Other crew chiefs asked McGee about his modifications. Pilots asked their crew chiefs to make similar adjustments. By mid-March, according to the group's maintenance records, more than 20 P-51s at Debden operated with enriched high-altitude fuel mixtures. None of this was officially authorized. The modifications violated technical manual procedures. They had not been approved by 8 Fighter Command, by the Materiel Command Engineering Staff, or by Packard Motors. Squadron and group commanders looked the other way, prioritizing combat performance over procedural compliance. Then came the combat test. March 6, 1944. 8 Bomber Command launched its first large-scale raid against Berlin. The mission plan called for 730 heavy bombers, B-17s and B-24s, to strike aircraft factories and rail facilities in the German capital. Escort would be provided by P-51 groups, including the 4th Fighter Group from Debden. Mission records preserved at the Air Force Historical Research Agency document the operation in detail. The bomber string stretched across hundreds of miles of European airspace, requiring coordination of multiple fighter groups providing escort at different stages. The 4th Fighter Group's assignment placed them with the bomber formation over northern Germany and Berlin itself, precisely where a Luftwaffe fighter opposition would be strongest. 48 P-51s from Debden took off at 10 o'clock hours. Of these, approximately 20 had McGee's enriched mixture modifications. Contact with German fighters occurred shortly after the formation crossed into German airspace. Captain Don Gentile's combat report, filed after the mission, described the engagement. Encountered approximately 40 Me-109s at 27,000 feet southwest of Berlin. Enemy aircraft attempted to climb above bomber formation. Gave chase. Found aircraft acceleration and climb rate noticeably improved from previous missions. Close distance on Me-109, despite initial altitude advantage. Engaged and destroyed 1 Me-109. Gentile's report was one of 14 filed by 4th Fighter Group pilots that day. Of the 14 pilots who claimed aerial victories, 9 were flying aircraft with enriched mixture modifications. Their reports consistently noted better than expected performance at high altitude. All aircraft returned to base. Post-flight inspections revealed no engine failures, no abnormal wear, no maintenance issues related to the fuel mixture changes. The success couldn't remain unnoticed indefinitely. By late March 1944, maintenance officers at 8 Fighter Command Headquarters began receiving reports about unauthorized engine modifications at multiple fighter bases. The 4th Fighter Group wasn't alone. Other groups had heard about the mixture enrichment and implemented similar changes. On March 28, 1944, according to records at the Air Force Historical Research Agency, 8 Fighter Command issued a directive ordering all P-51 units to return fuel mixture settings to technical manual specifications pending engineering review. The directive cited safety concerns and the need for proper testing before fleet-wide implementation of any modifications. Colonel Don Blakesley, commander of the 4th Fighter Group, responded with a detailed memorandum defending the modifications. His memo, preserved in the group's historical files, argued, "Combat results over the past 3 weeks demonstrate measurable improvement in high-altitude fighter performance. Pilots report consistent advantages in climb and acceleration above 25,000 feet. No engine failures have occurred. No maintenance issues have emerged. Request permission to continue current procedures pending formal engineering evaluation." Blakesley's memo included performance data compiled by the group's engineering officer, statistical analysis of combat results, and pilot testimonials. The evidence was sufficient to prompt formal investigation rather than immediate prohibition. April 1944, Wright Field, Dayton, Ohio. The Army Air Forces Materiel Command operated an extensive flight testing facility at Wright Field. Engineering officers there received orders to evaluate the fuel mixture enrichment modifications being used in European combat theaters. Technical reports from these tests, declassified and available through the Air Force Historical Research Agency, document the testing protocol. Engineers obtained a P-51B identical to those operating in Europe. They installed the same Packard V165 0-3 Merlin engine used by combat units. They modified the fuel system to match the enrichment levels reported from field units, approximately 15% richer mixture above 25,000 feet. Test pilots flew the aircraft through a comprehensive evaluation program. Testing measured rate of climb at various altitudes, acceleration times from cruise to maximum speed at different altitudes, engine temperatures under various power settings, and fuel consumption rates. Each test was repeated multiple times to ensure consistent data. Engineers compared results against baseline performance with standard mixture settings. The results confirmed field reports. According to the official test report dated April 18, 1944, fuel mixture enrichment of 15% above standard specifications for altitude. Operations above 25,000 feet produces the following measured improvements. Rate of climb increased by 320 feet per minute at 27,000 feet. Acceleration from cruise to military power reduced by 5.2 seconds at 28,000 feet. Maximum speed increased by 14 miles per hour at 30,000 feet. The report continued. Engine temperatures increased, but remained within acceptable limits. Cylinder head temperatures averaged 60 degrees Fahrenheit higher than standard settings, but did not exceed maximum rated temperatures. No detonation observed. Spark plug examination after 15 hours operation showed heavier deposits, but no fouling. Engine teardown inspection after 50 hours operation revealed no abnormal wear patterns. The engineering conclusion was clear. The modification worked and was safe. But the report also noted a drawback. Fuel consumption increased by approximately 12% at high altitude settings. This reduces operational range and endurance when operating above 25,000 feet for extended periods. For bomber escort missions to Germany, this trade-off was acceptable. P-51s carried sufficient fuel to reach targets deep in Germany and return. Losing 12% of high-altitude endurance was worthwhile for gaining significant performance. Improvements in the altitude band where most combat occurred. Why hadn't Packard engineers discovered this in their original testing? The Wright Field report addressed this question directly. Packard's testing priorities during engine development focused on reliability, maintenance intervals, and fuel efficiency. The company needed to demonstrate that the V1650 engine could operate continuously for hundreds of hours between overhauls. They needed to show acceptable fuel consumption to meet Army Air Force's range requirements. To achieve these goals, Packard engineers deliberately conservative mixture settings that ensured long engine life and good fuel economy. The performance trade-off seemed acceptable given the P-51s' already impressive speed and range characteristics. But Packard's testing occurred before extensive combat experience revealed the tactical importance of high-altitude climb and acceleration performance. According to Dr. William Pauley, who worked on the Merlin engine program at Wright Field and later published a technical history of the engine development, the issue was one of competing priorities. Packard optimized for engine longevity and operational range. This made sense for a long-range escort fighter that needed to fly deep into Germany and back. But combat revealed that brief periods of maximum performance at high altitude could determine mission success. Trading some fuel economy and potentially shorter engine life for better combat performance proved worthwhile. The Wright Field testing showed that engines could tolerate the richer mixture without immediate failure. Long-term effects might include shorter intervals between overhauls, but in combat operations, this was acceptable. May 1, 1944, 8th Fighter Command issued Technical Order 016OJ-E57. The order, preserved in National Archives records, authorized fuel mixture enrichment for all P-51B and P-51C aircraft operating in the European theater of operations. The order specified the exact mixture adjustment procedures, pilot operating guidelines, and maintenance inspection requirements. Every P-51 squadron received detailed instructions. Crew chiefs across dozens of fighter bases performed the modifications. Within 2 weeks, more than 500 P-51 Mustangs operated with the enriched mixture settings. The order credited the 4th Fighter Group with identifying the modification through field experimentation. It did not name Technical Sergeant Charles McGee specifically. Combat records from May and June 1944 document the impact. 8th Fighter Command statistical summaries, compiled monthly and preserved in the Air Force Historical Research Agency archives, show measurable changes in air combat results. In March 1944, before widespread mixture enrichment, P-51 groups claimed 3.2 aerial victories for every aircraft lost in combat. In June 1944, after Fleetwide implementation, that ratio increased to 4.7 to 1. This improvement resulted from multiple factors: pilot experience, numerical superiority, declining Luftwaffe capabilities, but performance improvements from mixture enrichment contributed measurably. Pilots consistently reported better combat performance at high altitude. Mission reports described improved ability to pursue German fighters in climbs, faster acceleration in combat situations, and better overall combat effectiveness. The modification that began as one crew chief's unauthorized experiment had become standard procedure across every American fighter squadron in Europe. Technical Sergeant Charles McGee never received official recognition for the fuel mixture modification. No commendation appears in his personnel file. No medal was awarded. His name doesn't appear in 8 Fighter Command's official histories or in the 4th Fighter Group's wartime records beyond routine maintenance documentation. According to Colonel Blakesley's post-war interview, preserved in the Air Force Oral History Collection, this was deliberate. We didn't want to highlight that one of our mechanics had violated tech manual procedures, even if it worked out well. The official story was that engineering discovered this through systematic testing. Charlie understood. He wasn't looking for glory. He just wanted our pilots to have every advantage. McGee continued working as a crew chief through the end of the war in Europe. His efficiency reports, maintained in the National Archives, consistently rated him as excellent. He was promoted to Master Sergeant in September 1944. After Germany's surrender in May 1945, McGee returned to the United States. He was discharged in November 1945 and returned to civilian life in Ohio. The mixture enrichment modification continued in use through the end of the war. When North American Aviation developed the P-51D model with the Packard V16507 engine, engineers incorporated richer high-altitude mixture settings as standard. The P-51H, the final production version, used even more aggressive mixture curves based on continued combat experience. The fuel mixture story illustrates a persistent pattern in World War II military technology development. Formal engineering processes emphasize safety, reliability, and conservative performance estimates. This approach made sense equipment failures in combat could be catastrophic, and systematic testing helped prevent them. But combat-created performance demands that peacetime testing couldn't always anticipate. Frontline personnel, pilots, mechanics, technicians encountered specific tactical problems and developed practical solutions. These solutions sometimes violated established procedures, but addressed real operational needs. When field modifications proved effective, the military establishment faced a choice: suppress unauthorized innovation or validate and implement it. In many cases, including the P-51 mixture enrichment, the military chose pragmatism over procedure. Other examples followed similar patterns. Bomber crews in the Pacific discovered that removing waste gun positions and ammunition reduced weight and increased range, allowing B-24 groups to reach targets previously beyond their reach. This violated Army Air Force's regulations about defensive armament, but proved tactically sound. Tank crews in Europe welded additional armor plates to Sherman tanks using salvaged metal, creating makeshift protection against German anti-tank weapons. The modifications weren't officially approved but spread across armored divisions because they saved lives. Artillery crews discovered that mixing different powder charge combinations could extend gun range beyond technical manual specifications. While potentially dangerous, these modifications provided tactical advantages in specific situations. The pattern repeated. Frontline personnel identified problems, developed solutions, tested them under combat conditions, and spread successful innovations through informal networks. Official channels then validated and standardized what was already occurring in the field. Packard Motors engineers eventually studied the mixture enrichment modification in detail. According to company records preserved at the National Automotive History Collection in Detroit, Packard conducted extensive testing in late 1944 to understand the long-term effects of richer high-altitude mixtures on engine reliability. The results showed increased cylinder wear and slightly shorter intervals between required engine overhauls. Engines operating with enriched mixtures needed major maintenance after approximately 250 hours instead of the standard 300 hours. But in combat operations, this proved insignificant. Fighter engines rarely accumulated 250 hours between overhauls anyway. Combat damage, bird strikes, and routine maintenance needs meant engines were regularly removed and rebuilt. The slight reduction in overhaul intervals had minimal operational impact. Packard incorporated the enrichment data into later engine versions. The V1650-7 engine, introduced in 1944, included carburetor modifications that made enriched high-altitude operation standard rather than a field modification. The company never publicly acknowledged that the modification originated from a crew chief's field experimentation rather than their engineering department. After the war, the fuel mixture enrichment story faded into technical obscurity. Aviation historians focused on aircraft design, pilot achievements, and major technological breakthroughs like jet propulsion and radar. Minor modifications to existing engines received little attention in historical accounts. Charles McGee's role remained unknown outside a small circle of veterans who served with him at Debden. In 1997, McGee's son donated his father's wartime notes to the National Museum of the United States Air Force, a museum curator researching P-51 maintenance procedures discovered the notes and began investigating their significance. Cross-referencing McGee's notes with official records revealed the connection between his field observations in early 1944 and the subsequent technical orders authorizing mixture enrichment. The museum published a brief article about McGee's contribution in its quarterly research journal in 2001. The article reached few readers outside the military aviation research community. McGee himself had died in 1989, never having spoken publicly about his wartime work. According to his son's interview with the museum, McGee considered his contribution minor, just a crew chief doing his job. Modern aerospace engineers studying the episode identified several lessons about aircraft performance optimization. First, manufacturer testing priorities don't always align with operational needs. Packard optimized for reliability and efficiency-appropriate goals for peacetime commercial engines or for preliminary military testing. But combat operations prioritize peak performance during brief critical moments over long-term efficiency. Second, field personnel operating equipment under real conditions often understand performance characteristics that laboratory testing misses. McGee's observation that engines ran below their thermal limits at high altitude came from daily experience with actual combat aircraft, not controlled test conditions. Third, systematic testing validates field innovations. McGee's modification worked, but Wright Field testing confirmed why it worked and established safe parameters for widespread implementation. Field innovation and formal engineering aren't opposed, they complement each other. These lessons applied beyond World War II aircraft engines. Modern military aviation continues to balance manufacturer specifications, engineering testing, and field experience. Pilots and maintenance personnel still discover performance characteristics that weren't apparent during development. Formal testing still validates and refines field innovations before wide implementation. The fundamental tension between conservative engineering and aggressive performance optimization remains relevant. Behind the technical story lies a human dimension worth noting. Charles McGee was 22 years old when he made the fuel mixture modification. He had no advanced engineering degree. His training consisted of Army Air Force's technical school and on-the-job experience maintaining aircraft. Yet he questioned established procedures, formed a hypothesis about engine performance, convinced his commanding officer to authorize testing, and developed a modification that improved combat effectiveness for thousands of pilots. This wasn't unique to McGee. World War II mobilized millions of Americans, many young and without advanced education, and placed them in technical positions requiring judgment, initiative, and problem-solving ability. Crew chiefs maintained complex aircraft engines. Radar operators learned electronic systems. Bombsight technicians serviced precision instruments. Radio operators worked sophisticated communications equipment. Many brought civilian mechanical skills. They had repaired cars, fixed farm equipment, or worked in factories. They applied practical knowledge to military equipment, often discovering performance characteristics that formal engineering hadn't considered. The fuel mixture modification exemplifies how individual initiative, within a system willing to listen, could produce measurable results. McGee made observations. He formed a theory. He convinced someone in authority to test it. Testing validated his theory. The organization implemented his discovery. The system worked, not because military bureaucracy was efficient, but because specific individuals at different levels chose to prioritize results over procedure. By May 1945, when Germany surrendered, more than 5,000 P-51 Mustangs operated in the European theater of operations. Everyone used fuel mixture settings derived from Charles McGee's unauthorized experiment in March 1944. Exact measurements of the modification's impact on combat effectiveness are impossible to isolate. Too many variables affected aerial combat results: pilot skill, tactical situation, numerical advantage, enemy capabilities. But the consistent pilot reports, the measured performance improvements documented by Wright Field testing, and the rapid adoption across all fighter groups indicate meaningful tactical advantages. 8 Fighter Command statistical summaries show that after May 1944, P-51 groups consistently achieved higher victory-to-loss ratios at high altitude than before the mixture modification. This suggests the performance improvements translated into combat success. The documented facts are these. In February 1944, a crew chief at RAF Debden believed P-51 engines could run richer fuel mixtures at high altitude without damage. He convinced his squadron commander to authorize testing despite violation of technical manual procedures. Testing demonstrated improved performance with no engine failures. Other pilots and crew chiefs adopted the modification informally. Combat results showed measurable improvements. Official engineering testing validated the modification's effectiveness and safety. 8 Fighter Command authorized Fleetwide implementation. The modification became standard procedure across all American fighter operations in Europe. Later, P-51 variants incorporated the enriched mixture settings as factory specifications. The story matters less for its technical details than for what it reveals about innovation under pressure. Military organizations prioritize standardization and procedure for good reasons. Consistency prevents errors. Following established guidelines reduces accidents. Standardized maintenance ensures reliability. But rigid adherence to procedure can prevent adaptation to changing circumstances. Combat constantly revealed problems that peacetime planning hadn't anticipated. Equipment performed differently under combat stress. Tactical situations demanded capabilities that original specifications hadn't prioritized. Enemy innovations required rapid responses. Effective military organizations balance procedural discipline with flexibility to adopt proven field innovations. The P-51 fuel mixture modification succeeded because the system allowed it to succeed. Major Goodson authorized initial testing. Colonel Blakesley defended the practice when headquarters questioned it. Engineering officers at Wright Field conducted objective evaluation rather than simply enforcing compliance. 8 Fighter Command implemented the change fleet-wide once testing confirmed its value. At each level, individuals chose pragmatism over rigid procedure. This pattern repeated throughout the war across all services and all theaters. Field personnel identified problems, developed solutions, and spread innovations through informal networks. Official channels validated and standardized what proved effective in combat. The alternative suppressing field innovation and enforcing strict procedural compliance would have prevented adaptation to combat realities. Aircraft engine performance optimization was just one of thousands of technical challenges American forces faced during World War II. The broader story of American industrial and technological mobilization involved millions of individuals at every level making contributions that ranged from profound to incremental. Some contributions came from formal research programs, radar development at the Radiation Laboratory, proximity fuse development at Johns Hopkins, atomic bomb development in the Manhattan Project. Others came from industrial engineering mass production techniques for aircraft, ships, and vehicles that enabled America to overwhelm enemies through sheer material superiority. But many contributions came from individuals like Charles McGee technicians, mechanics, operators, and crews who identified specific problems and developed practical solutions. These incremental improvements collectively made American equipment more effective than enemy planners anticipated. German and Japanese intelligence services understood American industrial capacity, but underestimated how effectively American forces would optimize that equipment through continuous field improvement. It's important not to overstate McGee's contribution. The fuel mixture modification didn't change the war's outcome. Allied victory resulted from overwhelming industrial capacity, geographic advantages, strategic decisions, and the fighting capability of millions of service members. The modification didn't even change aerial combat fundamentally. P-51s already outperformed most Luftwaffe fighters in most situations by early 1944. The mixture enrichment provided marginal improvement to an already superior aircraft. But marginal improvements matter in combat. A few hundred feet per minute better climb rate meant reaching altitude advantage slightly faster. A few seconds quicker acceleration meant closing distance on enemy aircraft slightly more effectively. These advantages, multiplied across thousands of combat encounters, saved lives and increased mission effectiveness. That was McGee's contribution, not decisive, but meaningful. In 2003, the National Museum of the United States Air Force installed an exhibit about P-51 Mustang maintenance and operations. A small panel in the exhibit mentions Technical Sergeant Charles McGee and his fuel mixture modification. The exhibit includes one page from his maintenance notes, showing his observation about engine temperatures and his question about running richer mixtures. Few visitors notice the panel. The exhibit focuses primarily on aircraft design, combat achievements, and pilot experiences, the conventional narrative of aerial warfare. But the panel exists, documenting one crew chief's contribution to American fighter effectiveness over Europe. March 1944 to May 1945, 14 months. That's how long the fuel mixture modification influenced American fighter operations in Europe. 14 months from unauthorized field experiment to standard procedure across thousands of aircraft. The modification originated because one mechanic questioned accepted procedures, convinced one officer to authorize testing, and demonstrated improved performance that others could verify. It spread because pilots wanted better performance, crew chiefs shared technical knowledge, and commanders prioritized combat effectiveness over procedural compliance. It became official because engineers tested objectively, confirmed the results, and the organization implemented what worked. No dramatic moment. No single battle where the modification proved decisive. Just incremental improvement that made American fighters slightly more effective in thousands of individual combat encounters. Charles McGee returned to Ohio after the war. He worked as an automotive mechanic until his retirement in 1979. He never flew in the aircraft he maintained. He never fired a shot in combat. He never commanded troops or made strategic decisions. But for 14 months, every American fighter pilot over Europe benefited from his willingness to question established procedures and test a better solution. That's the documented story verified through maintenance logs, combat reports, engineering tests, and official records. One mechanic, one modification, thousands of aircraft. Sometimes innovation comes from unexpected sources, succeeds through practical testing, and spreads because it works.